Hey everybody, how's it going? Today we're going to look at mass and mole conversions. Let's dive right into it. Our goals for today are to start off by practicing converting moles to molecules and vice versa. We'll do this using Avogadro's number, which you'll hopefully remember by the end of this unit. We'll then take a look at the concept of molar mass and how to calculate molar mass for a compound. We'll take a moment to look at the difference between molar mass and atomic mass, and then we'll practice some mass to mole conversions. Let's take a brief moment to refresh ourselves on Avogadro's number. Avogadro's number is 6.02 times 10 to the 23rd and represents the number of molecules or atoms in 1 mole. This means that Avogadro's number is a conversion factor, or a number that can be used to convert one unit to another. Much like 100 centimeters per meter is a conversion factor that can be used to convert meters to centimeters or vice versa, Avogadro's number allows us to convert from molecules to moles or vice versa. Let's try some practice. Now, before we get started with these example problems, I'm going to go ahead and write Avogadro's number up here. So 6.02 times 10 23rd, and then as atoms or molecules per mole. Now this first question asks us how many moles are in 1.204 times 10 to the 24th atoms of magnesium. So we have 1.204 times 10 24th atoms of Mg, and we want our answer to be in moles of Mg. Now, if we were to bring down Avogadro's number and use it like this, we would end up having atoms times atoms divided by moles, which wouldn't cancel out. So instead, we want to flip this number and make it 1 over. And that'll give us moles per atom. So it's 1 mole per 6.02 times 10 to the 23rd atoms. This is all we really did there. So if we multiply this by 1 mole divided by 6.02 times 10 to the 23rd atoms, these atoms will cancel out. I guess it should be Mg, and it will leave us with moles of Mg. So all we have to do now is to take 1.204 times 10 to the 24th, divide that by 6.02 times 10 to the 23rd, and that's going to leave us with 2. So for the answer to the first problem, we have 2 moles of magnesium. And the second question asks us how many moles are in 3.01 times 10 to the 24th molecules of carbon dioxide. And remember that the 6.02 times 10 to the 23rd can be in atoms or molecules. It works for either one. So we will do 3.01 times 10 to the 24th molecules of CO2, and we want to end up with moles, oops, that's okay, of CO2. Now in order to do this, we're going to want to do the same thing, times 1 mole per 6.02 times 10 to the 23rd molecules, and it'll be CO2, CO2. The units will cancel here, and we will be left with moles of CO2. And all we have to do here is take 3.01 times 10 to the 24th, divide it by 6.02 times 10 to the 23rd. I would suggest using a calculator for this because doing this on your own and in your head, or even out on pencil and paper, is going to take a while with all the scientific notation and stuff, but you will end up getting 5 moles here of CO2. And that's going to be our answer for that one. Now, going in the reverse direction is actually going to be easier. So again, Avogadro's number 6.02 times 10 to the 23rd, and that's atoms or molecules per mole. Now here we've got 3 moles of mercury, 3 moles Hg, and we want to end up with atoms of mercury. Okay, and in order to do this, all we have to do is multiply by Avogadro's number, 6.02 times 10 to the 23rd atoms per 1 mole, and these are all of mercury. And our moles will cancel, So all we're left to do is 3 times 6.02 times 10 to the 23rd, which is 1.806 times 10 to the 24th atoms of mercury. This next one asks how many molecules of ammonia are in 2.4 moles. So we have 2.4 moles of NH4, and we want to end up with molecules of NH4. This one, same deal, we just multiply by 6.02 times 10 to the 23rd, and that would be molecules of ammonia per 1 mole of ammonia. And when we do that out, we get 1.445 times 10 to the 24th molecules of NH4. Now, let's talk again about why Avogadro's number is important. Masses that we saw in the periodic table are listed in AMU, or atomic mass units. These are decidedly unhelpful to us, as they are far too small to measure. However, if we have 1 mole of a substance, we have the same mass in grams instead of AMU. For example, the atomic mass of hydrogen is 1.0078, so 1 atom of hydrogen has an average mass of 1.0078 AMU. 1 mole of hydrogen, however, has a mass of 1.0078 grams. For carbon, the atomic mass is 12.011, so 1 atom of carbon has an average mass of 12.011 AMU. 1 mole of carbon has a mass of 12.011 grams. The molar mass of a substance is the mass of 1 mole of a substance, and it is written in grams per mole. This, like Avogadro's number, can be used as a conversion factor, but the molar mass of a molecule changes depending on the type of molecule. For single atoms of pure elements, the molar mass is equal to the atomic mass in grams per mole. We looked at that on the last page. So hydrogen has a molar mass of 1.0078 grams per mole, and carbon has a molar mass of 12.011 grams per mole. For a molecule, however, the molar mass is equal to the combined molar mass of all of the elements in the molecule. Let's look at some examples. Now, all of these examples ask us to calculate molar masses, and in order to do this, we're going to need a periodic table handy. So, the first one asks, what is the molar mass of magnesium? Now, this is just elemental magnesium, and if we look on the periodic table, we see that its atomic mass is 24.305 atomic mass units. Since we're doing a molar mass of a pure element, all we need to do is write that same number, 24.305, and it is in grams per mole. And that one's pretty easy. You just need to take it from the bottom of the periodic table. The second one asks, what is the molar mass of table salt, NaCl? And so we know that the mass of sodium, the atomic mass, is 22.990. And the mass of chlorine, based on the periodic table, is 35.45. So in order to get the molar mass of table salt, which is sodium chloride, we just need to add these two numbers together. So we have 22.99 plus 35.45, which gives us 58.44, and that is again in grams per mole. Now this last one asks us what the molar mass of copper chloride is. So if we look at the periodic table, we'll see that the mass of copper is 63.546. 63.546. And the mass of chlorine is still 35.45. Now in this case, there are actually 2 chlorine atoms in each molecule of copper chloride. So we need to multiply this one by 2, and then we're just going to add these together again. So we have 63.55, I'm going to round up, plus 35.45 times 2. And all of that will equal 134.45 grams per mole. So again, all we're doing is taking the atomic mass of each element in our substance, the number of element occurrences within that substance, we'll multiply this by, and then we just add those together, and that'll give us our molar mass. Much like we used Avogadro's number as a conversion factor, molar mass can also act as a conversion factor. While Avogadro's number allows you to convert from molecules or atoms to moles, molar mass allows you to convert from grams to moles. Let's do some practice examples. Our first set of example problems asks us to convert from moles to mass. So, first question asks how many grams of carbon are in 0.5 moles. Now, in order to do this, we first need the molar mass of carbon. And we know that the molar mass of carbon is 12.00011 grams per mole. If we have 0.5 moles, and we want to get to, moles, and we want to get to grams, then we need to make sure that our conversion factor will be such that the units are going to cancel out. And in this case, it's already lined up correctly. So we have 12.011 grams per mole. That's 1. Moles will cancel out. So we get 0.5 times 12.011, which is 6.005 grams. The second one asks how many grams of carbon dioxide are in 3 moles. So again, we've got 3 moles, and we want to end up with grams. Now, in this case, carbon dioxide, we're going to need to calculate the molar mass. Since the molar mass of carbon is 12.011, and oxygen is about 16, I'm going to go ahead and round off carbon as well, so that we just use 12. We've got 12 for our carbon. There's just 1 carbon. There are 2 oxygens, so that'll give us 32. And 32 plus 12 gives us 44 grams per mole of CO2. So then we use that conversion factor, 44 grams per 1 mole. Moles will cancel. 3 times 44 is 132 grams. This last one asks how many grams of magnesium are in 2.8 moles. And magnesium has a molar mass of 24.305 grams per mole. We've got 2.8 moles. We want to get to grams, and we know that it is 24.305 grams per 1 mole. Moles will cancel, and we are left with 2.8 times 24.305, or about 68.1 grams. Now this next set of example wants us to go the other way. So in this case, we're going from mass to moles. First one asks how many moles of sodium are in 46 grams. First and foremost, we need to once again get our molar masses. So for sodium, it is 22.99, or I'm going to round up to 23. So Na is 23 grams per mole. Now in this case, we have 46 grams, and we want to end up with moles. So all we're going to do is flip this number here. So we have 1 mole per 23 grams, and the grams will cancel. So we get 46 times 1 divided by 23 equals 2 moles of sodium. For this one, we've got ammonia, which is NH3. So first we need to calculate the molar mass of that. And again, doing some rounding, we've got hydrogen has a molar mass of 1, nitrogen has a molar mass of 14, and there are 3 hydrogens in here. So we'll get 3 plus 14, which is 17, is our molar mass of ammonia, and again, that is in grams per mole. So in this case, we have 136 grams. We want to end up with moles. and it's going to be times 1 mole per 17 grams. Grams will cancel out, and we get 136 divided by 17, or 8 moles of ammonia. And for this last one, we're doing how many moles of carbon dioxide are in 4.4 grams. And again, we said that carbon dioxide, we calculated this in the last one, had a molar mass of 44 grams per mole. In this case, we have 4.4 grams. And we want to get to a number of moles. Multiply that by 1 mole per 44 grams. Grams will cancel. We get 4.4 divided by 44, or 0.1 moles. There will be some practice worksheets for these types of conversions if you want extra practice, and I will probably release a separate video for practicing these conversions as well as volume to mole conversions later in the week. Let's take a moment to review what we covered today. We looked at using Avogadro's number as a conversion factor to convert between molecules or atoms and moles. Molar mass, which is the mass of 1 mole of a substance, with units of grams per mole, is also a conversion factor, and can be used to convert from mass to moles and vice versa. This allows us to convert masses to moles, which can be used in balanced chemical equations to determine ratios of elements, but we'll look more at that later. That's it for today's video, and I'll talk to you all later.